let's run through these definitions. You don't have to write this, you have it already. You can make a little notes in your book. I'll show you those two important things to write, right? First thing first, so if I give you a function, right? A function f from a set A to a set B assigns to A, which is an element of A, f of A in the set B. That make any sense? That make any sense? Right, so here what it's saying, right? What it's saying is that A comes from this set A, right? And if you find that f of A will belong to the set B. That make any sense? Right? So in a function basically takes a set of values A and it maps that set of values to B. But okay with that? That's simple, right? So it takes a set of values A and maps it to B. So here's what it says. If I were to take a value from B, let's say from A, let's say the value is lowercase a. And I were to take lowercase a and put it into the function, what I will end up with is a value in the set B. That makes sense? Right, let's do my favor and read over line 1. See if it makes sense now. See if line 1 makes sense. A function f from a set A to a set B assigns to each lowercase a an element of A, a single element f of A in the set B. That makes sense? Right? All this saying is that f of A, whatever value you take from capital A, whatever value you take from capital A will belong to capital B. That's all. Okay? I think that's a little much jargon, right? But all this saying is that anytime you find f of A, that value will belong to the set B. Okay? The element in set B is called the images. So if you remember your Form 5 stuff, you might remember something like this. You take a set of values, let's call them A, and you map those values onto a set of values called B. That's okay? All the values in A are called your domain, and all the values in B, provided that they have mappings to them, are called your images. Right? We also call that set of images your codomain. That's okay? Right? The range of the set of the elements that are in A are the images, right? So your range is all the images. I'm not sure if you remember this, but sometimes this could happen. Let's say you have the values 1, 2, 3, 4, and you have A, B, C, right? A is mapped to 1, B is mapped to 2, C is mapped to 3. What do we call ABC? That is the what? Domain. What do we call 1, 2, 3, 4? Your codomain. Right. What are the images here? 1, 2, and 3. So what do you call 1, 2, and 3 again? The set of images are called your range. Got to clear that? Yeah. So ABC, we call that your domain. 1, 2, 3, 4, codomain. 1, 2, 3 images, and those set of images are also called your range. That's okay? Yeah? All right. So in your notes, I want to write that, right? Because some of you all looking at the first time you hear that. Or they somebody could see it. Right. Right. So this one, if A is mapped to B, right? And we have all of this here. We have A, B, C, and we have 1, 2, 3, 4. A is mapped to 1, B is mapped to 2, C is mapped to 3. We call the set A, B, C. We call that set a domain. Call 1, 2, 3, 4. That set is your codomain. right? 1, 2, 3. That is set of images called your range, right? Okay, so just important to understand the difference between domain, codomain, and range. Is the codomain the same as the range in our example? No. You'll remember the 4 types of mappings: one to one, one to many, many to one, many to many, right? Quick question, right? Which set their capital E? Which set up their capital E? Which one? Maybe. Which set is capital B? 1, 2, 3, 4, right? Right, nice. What do we call, or what do we call A1? What do we call B2? And what do we call C3? What is call those values? What is call them? Order pairs. Right? So we call all of these here your ordered pairs. Okay? Make a note of that. Your ordered pairs. All right, nice. How do we represent a function? Right? Function can be described using arrow diagrams, like I showed you just now. That's a relation diagram. Functions can be described using ordered pairs. A function can be described using a graph, a formula, or a list of values. Okay? Right. So we have 2 tests that we need. Well, 1 test that we use to determine if a function actually exists. All right. So now because you write something with a nice little formula like this. Now because you write something with a nice little formula like this, right? This is a function, right? Right? Not every little formula or algebraic expression is actually a function. So what we have to be able to do is to do a test, do a sketch, and then do a test. So the test that we generally use, we call it the vertical line test. So if a vertical line is drawn parallel to the y-axis, oh, continue. So if a line drawn parallel to the y-axis cuts the graph at most once, the relation is a function. All right. So for example, we look at the second diagram, look at the first diagram. When I did the vertical line test, it would recognize that the line touched the curve twice. So therefore it is not a function. I have a quick question. What type of mapping is that? What type of mapping is this function in? What type of mapping? One to one, one to many, many to one, or many to many? What do you all think? Online? Tell me what you think now. What type of function it is then? I'll tell you how to figure it out just now. What type of function you think you have there? One to one, one to many, many to one, or many to many? Let me come somebody. Jesse, what do you think? One to many. What do you think? Many to one. What do you think, Victoria? One to many. All right. So let's see. One to many means one x value to many y values. Right? Many to one means what? Many y values to, yeah. Many to one means many x values to one y value. Right? I want to say it wrong. All right. So let's see what we have here. Let's take this one x value here. That one x value has a y value here and a y value here. Right? So that x value has a mapping to y1 and it has a mapping to y2. So one x value going to y1 and to y2. So that type of mapping is one to many. That's okay? So a one to many mapping is your first example, is your first function there. One to many. Right? One to many is not a function. Okay, so make a note of that, please. One to many is not a function. Any answers online? Nothing from online, right? Who online then? Upa, Ariane, Bradley, Michelle. Where are monkeys? What happened? Right now. Right. Are you okay with that? Yeah. And of course, if you do the vertical line test and it only touches the function once, then the function is one to one, and then the function exists. Okay? So please remember that vertical line test, and please remember how to sketch. All right? This one is one to one. Right. How do we know if a function is injective now? To show a function injective, basically it means that the function is a one-to-one mapping. Okay? So a function fx to y is injective if every element of y is mapped onto by one and only one element in x. So for example, a one-to-one function, every value in, let's say this is 1 and 2, 7 and 8. Every value in x is mapped to one value in y, and well, one value in y is mapped to one value in x. Okay? So how do we show a function is one to one? Let's make a note of this. To show a function is one to one, we can use the mathematical method. If f of a equals to f of b, then f of a and b equal. I'll show you an example shortly. Or you do a line parallel to the x axis and see if it cuts once. Right? So method one is the formula. Method two is called the horizontal line. Yes. And the elements and any group as well. But just make a note of that because I'll do some questions on that. All right. Finish. Wrap it up. Right, and just taking note for subjective one time, so I'll start with questions, right? All right, party one die. Right, so we need to determine if functions are one-to-one and if functions are subjective. Right, one-to-one generally simple. The hard thing is subjective at times. How to show subjective, they could give you some challenging questions on that. One-to-one, not so bad. Right, I like the graphical methods, that's the reason why I showed you all the sketch tools, right? One to remember those four curves, they should be okay. And the transformation. Right, method one, you can use it, method two, I like method two more. Method two is also called the horizontal line test. Okay? Method two is also called the horizontal line test. Right, next thing, how do we show subjective now? Right, so to show one-to-one, you can use our little formula, I'll show you that now. Right, plug in A and B, and then next you can sketch a graph and do a horizontal line, right? And last thing that we need to remember in functions, we need to remember how to show a function onto. Onto means subjective, right? Basically, subjective implies that right, codomain and the range is the same. Okay, so make a note that onto or subjective implies that the codomain of the function is equal to the range of the function. Right, codomain equal to range. Right, there are two techniques. Number one, just look at the codomain, look at the range, and see what they say. Right, that's if it's actually available. If it's not, you will have to use this technique here, right? A line drawn parallel to the x-axis must cut at least one straight to beyond. Okay, and I'll show you our next technique by rearranging the formula and checking to see if any possible value of x will give you a function of y that is not any codomain. No. All you writing is onto codomain equal to range, right? Compare the codomain equal to the range. Let's do a couple of examples on code before I update the some password. Right, the next thing with function that we have to remember is the form 5 stuff, and I will show you that well, right? What does bijected mean again? Bijected means that is both onto one 1-to-1, right? All right, so let's write that, right? What is 1-to-1, what is onto, and what is bijective? Bijective means that the function is 1-to-1 and onto. Ready? Take it off, right? All right, let's do it, right? Let us see what we get in here. All right, so number one. So let's say we have a function looking like this, right? If we have f of x is equal to 5x minus 1 between 0 and 4, right? Let's see if we can determine. Let's see if we can determine if it's injective, right? And I'll do both methods, right? So let's see if it's injective. So method one, right? Method one, here's what we're gonna do. Method one says that if we find f of a and we make it equal to f of b, then we should get a being equal to b, right? If it's 1-to-1. So here's what this says. This saying, if I put a in here, I will get 5a minus 1. If I put b in here, I will get 5b minus 1. And if I simplify this, I am supposed to get a equal to b. If I don't get a equal to b, not 1-to-1. Okay, so let's see. Carry across the 1, I'll cancel. I'll get 5b is 5b, divide both sides by 5. I'll get a is equal to b, therefore 1-to-1. That's okay? That's method one. Method two has to do with method two has to do with the graphical approach. Right? We could do a quick little sketch from 0 to 4. What does it look like? When x is 0, again minus 1. When x is 1, I get in 4. So it might be going up like that, right? Right? That is the function f of x. What do we do now in method one? What do we do now? Method two, I mean, sorry. What do we do? Draw. Second back first. Draw a horizontal line. Draw a horizontal line. And see if the horizontal line will cut more than once. Would it cut more than once? No. Right? So therefore, it passes the horizontal line test. passes the horizontal line test. Therefore, it is injective or one-to-one. All right, copy it down. Let's try the next function. Try that there. Right, try this next function using both methods. Right, try f of x equal to x squared using the next method, using both methods, 1 and 2. Finish? I gave you a domain, right? Pay attention to it. I gave you a little domain there for a reason, right? All right, ready? Right. So here what it's saying, right? This saying f of x is equal to x squared, right? F of x is equal to x squared, and we're only interested in the part more than 0. All right. So ideally, I should do method 2 first for you, right? Before I do method 1. All right. So I'm just going to try method 2 here for you. So you'll have a better picture of what I do in method 1. Right? Method 2, we're going to sketch x squared. X squared looks like this. But I said x squared, but x is more than 0. So you take this part off, you draw a little hollow circle there, right? You draw a little hollow circle there, right? And you go all the way up. The reason it's hollow is because 0 not included here. Okay? Then, if I do a horizontal line test, can I draw a horizontal line anywhere and make it cut more than once? Make it cut more than once? No. Therefore, this function is 1-to-1, right? But it passes the horizontal line test. Or we could say this is method 1, right? Or we could say f of a is equal to f of b. We could say that, sorry, put a in here, you'll get a squared minus b squared, right? When you carry across the squared, you'll get square root, right? What's the square root of b squared? Huh? Plus and minus b, right? But remember, x will only be negative. So since b is more than, sorry, b could only be positive. Since b is more than 0, a is equal to b, therefore 1-to-1. Are you okay with that? Yeah, that's the only reason why this function is 1-to-1. Otherwise, normally what? Normally a quadratic is, right? It's not 1-to-1. We're going to say 2-to-1. Yes. Let us see if let us do over these now and see if they are onto. Or Roberto. All right, quickly. So what you see? One of the ways for us to check and see if a function is surjective or onto. One of the ways is this, right? If I gave you a function, y is equal, well, f of x is 5x minus 1, I could also write it like this. Y is equal to 5x minus 1, right? Remember, on two implies that something like this, right? If the codomain is ABC, if the codomain is ABC, then the range should also be ABC, right? So it means that every value, X value has a corresponding Y, and most important, every Y value, Ishana, every Y value has one and only one mapping. All right, that's okay. So what we're going to attempt to do is we're going to try to make X the subject of the formula. So you can do that mentally, right? X is equal to Y plus 1 on 5. That's okay. And then, based on the values given, we're going to check to see if any Y value, right? Any Y value you can put in here that will not give you X value in that range. Any given range, right? So check to see if any Y value can be substituted, right? And give a X value that is not in the range, right? So for example, the problem is we need to know the Y values for this case. Normally, what they do is this. I'm gonna give you one that I would normally see, right? F of R, right? You have all the R values mapped to R, right? These are X mapped to Y. So is there any real value I could put in here that will not give me a real value? Is there any real value I could put in here that will not give me a real value? Any real value? No, right? So what that implies, if there is no Y value I could put in here that will give me an X value that is not real, then I could say this implies that F of X is onto. That's okay? So all you're looking for is something like a proper contradiction. You're looking for a Y value that will not satisfy the X values given. Okay? But if they give you a domain and a range, it's easier for you to figure it out as well, right? So this question, are they okay with if it were R versus R? Yeah. But this question was what? Like I leave enough, right? This question was all the X values between 0 and 4. And we did a nice little plot. So this question, the ideal solution would have been the graphical method. So after you draw it, what did I say to do? Do the what? Check and see. Check your notes and see. I said to do a particular test. Do the horizontal line test again. So if I draw a horizontal line here, I draw a horizontal line here, it only cuts in once. Therefore, function is f of x is onto. Okay, so either method can work. All right, any method can work. This one is the better method for this question because it can sketch it graphically. We do have a codomain in this case. Okay. Right? So we're going to tackle something like this up. Ready? So let's take a look at this one here, right? For if f of r mapped to r is defined as f of x is equal to 3x squared minus 2x, is f of x on 2. Right? How are we going to do this? What's the best technique for us to try? I'm trying to do it this way. If we let y equal to 3x squared minus 2x, can you make x supplicate the formula here? And I had it. What we can do to make x supplicate the formula? What you can do? There is something that we can do to this before we make x supplicate the formula. Okay, that's where I here differentiate too. Right? What we can do is complete this square. Right? What we can do is complete this square. Okay? So to complete this square, you'll get y is equal to a by x, minus h squared plus k. H is b on 2a, so that's minus 2 on 3. 3 by 2 is 6. Minus 1/3, and k is c minus a h squared. So that will be c is 0, a is 3, and h is minus 1/3 squared. That'll be 1/9. That'll cancel, so you'll get positive 1, 2. So you're getting y is equal to 3 by x plus 1/3 squared plus 1/3 again. All right, this is minus, sorry. This is minus 1, 3. All right, good. Now let me show you working. I forget how to complete this square. Right, when you reach here, you can make x supplicate the formula. Make x supplicate the formula you feel. Come away again. Right, so here's what you're doing for me, right? When it comes to the square, make x the subject of the formula and check and see if any y value will mess up this relationship here. If any y value will mess up that relationship. Finish already? Make y the subject of, make x the subject of this. Subject and see if any y value, right? So if we have x value, that's fine. And if you want, you can multiply everything by 3 if you want, right? Right, but we're just trying to make x the subject. So it's 3 by x minus 1/3 squared. Carry across. Wait, you watch. You know you do it already. Right? Carry across the minus 1/3 and you'll get plus 1/3. What's the next step? What's the next step? Divide everything by 3, right? So x minus 1/3 squared is y plus 1/3 over 3. Right? Then you can carry across the square root. Yeah. So you'll get x minus 1/3 is the square root of y plus 1/3 over 3. And then carry across that minus 1/3. So you'll get x is equal to the square root of y plus 1/3 on 3 plus 1/3. Right? I know it's looking a little hard. If you wanted, right? If you wanted, you can multiply everything like 3 and make it look a little bit nicer. Right? So for example, here, multiply this by 3, this by 3, this by 3. Okay, and you can make it look a little bit nicer if you want. But here's the problem, right? The problem is we need to check and see if the function is on 2. Is there any y value I can put here that will give this no solution or no x value that is not real? Listen again, right? Is there any y value I can put here that will make that will give me an x value that is not real? X is what? What you want to put? Think about it. What y value I can put there? Any value, it don't matter. Any value there. Right? I know you're looking kind of bad there, but if you want, you can multiply it by 3 and figure it out, right? And change it around. But what value for y I can put here that will make this not have a solution? The only way this can not have a solution is watch and finish. To make this not have a solution. Square root of a what? A negative value, right? So once I can make this negative by a particular y value, then this will have no real solution. Correct? So we'll just make up any y value. Huh? 94? -4, yeah, that could work. If y is -4, right? If y is -4, we end up with a square root of a negative value. Therefore, no real solution. Okay? So when y is -4, there is no real solution. Therefore, there is no x value when y is this. Okay? Okay, so no x value corresponds, or no x value, let me use corresponds. No x value is mapped. No x value is mapped to -4. Therefore, the function is not onto. That's okay? Or what else we can do? Next method is to sketch this. Okay? The next option is to sketch this. More than likely, you'll get a minimum and you do the horizontal line test. Okay? But the problem with the horizontal line test, it will touch more than once. Therefore, not onto. Okay? Any method will work. Okay, but I just wanted to show you one that's a quadratic and what you have to do. Okay, so if you can sketch it, go right ahead and do the horizontal line test. Otherwise, make X the subject and check for a value for y that does not have a pattern. Okay, copy it out. So what does this mean, Selena? Would this function number 2 have a will this function be bijective? Would a function like this be bijective? No, right? Because it must be onto and onto one, right? So a function like this will not be a function like this will not be bijective. If y is equal to -4, we have a negative square root, which means no real solution. Negative square root. We have a negative square root, right? Now, you wanna record time? You wanna phone or you can do it? Can you do it? Alright, let go again now. This one is a past paper. So I'm gonna give you a function. You have to determine if it's one-to-one, if it's on-to, and if it's bijective. Alright? Right, but you would have to remember something from last week, right? Okay, so you have to determine if the function is bijective. Right, take your time, do the injective first, right? And then do a little sketch and figure out if it's on-to. Take your time, right? Just remember to sketch this. How to sketch it. What you do here? What something I do first. Right, so yeah, but it's something I do to get it into that format. What you have to do, long the gun. Right? So you can sketch it, right? But I want you to try method one here, right? See what happens. Do a little sketch and determine if the function one-to-one, if the function on-to. Sketch will tell you everything. So check for injective first. Right? As I said, you can use the formula f of a equals to f of b. For on-to, try the graphical way, right? Ready? Team message med igen. Ja, det message man kan säga kommer någon man ser. Right, try the f of b method, and then you just get to the next one. But you will also see it graphical. So look back at how we did the graphical part as well. That's like one line along division. Any answers online? Finish us. Catch you some last week. Right. Oh. Yeah, I have one. Oh yeah, do the sketch. I'm gonna work it out. What's supposed to give you for 5 minutes? Okay, I'll give you 5 minutes after this one, and I'll just run over the CXC stuff, right? Keep talking. What volume will you do? Right? So you would have a plus 3 over a minus 1, b plus 3 over b minus 1. Online, what you all got for this? Was it bijective? Cross multiply, you'll get a plus 3 by b minus 1, b plus 3, a minus 1. So I have ab plus 3b minus 3 AB plus 3A minus 3. Minus B, sorry. Right, this will cancel, minus 3 will cancel. Bring the A's on. I'm missing an A and minus A here, sorry. Bring the A's on one side, you'll get 3A minus A. Bring the B's on one side, minus B minus 3B. Here you will get minus 4A and minus 4B. Divide by minus 4, you'll get A is B. Therefore, 1 to 1. Right? But you could also show it graphically as well, right? But how do we get the graph now? Well, we have to long divide. We have to divide x minus 1 into x plus 3. Divide that method, should we? X into x is 1. 1 by x is x. And then you minus and you'll get 4. Right? So you'll end up with 1 plus 4 over x minus 1. Okay? You have to sketch this. So how do I sketch this? Well, I have to start with the base function, 1 on x. And the transformations are, number 1, we're going upwards 1. Number 2, we're going to the right 1. And then this just means stretch, right? A vertical stretch by 4, right? But you can't really show that, right? You can't really show this stretch on your graph, right? Because there's nothing to really compare it to, right? So it's going up 1. So your new asymptote is y is 1. It's going to the left 1. So your new asymptote is x is 1, right? And then we do the sketch, right? That is your sketch, right? How am I going to, obviously, we can see the horizontal line test here for 1 to 1, right? If I draw a line anywhere, it'll only cut the function once, right? But watch this particular line here. If I draw the line y is equal to 1, is there any corresponding x value? No, right? So when y is 1, or I can say when y is 1, it has no mapping. It has no mapping to x, therefore not on. Okay with that? So once you could draw a line that doesn't cut the function, right? Or doesn't cut the function. So once you could have a y value that has no x value, that means same thing there. Same thing there. You have a y value of -4 with no x value. Have a y value of 1 with no x value. That means this is not mapped to anything. So therefore the function is not onto. Everybody okay with that? Everybody okay with that? Yeah? Okay. Take a 2-minute break and then we'll take 5 minutes and then we'll take a look at the form 5 stuff that you need to remember on functions, right? How to find inverse and composite functions. Right? It's important to all because it's the most popular function that is given. Okay? Suppose I ask you to find the inverse of this one. Can you do it? Graphically. No, you don't flip it, you do something else. What you do? Reflecting. Inverse of this. N. No. No. In the line y equals x. So you draw the line y. Remember, I showed you that in logs and it. Nah. Remember that. Hey, wait, look at Gary's response online here. Somebody paying attention. Put a Chelsea. All right, nice. Oh, and Chelsea. Very good, Chelsea. Actually, Gary's response. Nice, Chelsea. Nice to know you're paying attention. Chelsea new, right? Very good, Chelsea. Keep that. All right, so take a 5 minutes and then we look at the form 5 stuff, right? We still have more questions to do in functions. When I review in module 1 with past papers, we'll do all the questions, right? But this is the most popular function, the one that looks like this. Okay, we take a 5 minutes and then we start. One of them one. Yeah, keep it going. Where's the one? I start back now. Right, I just go in about it from 5 stuff, right? How to find it, how to find it. All right. The last thing that we're going to take a look at is take a look at some functions, right? All right. So let's take a look at inverse, right? And we know that for a function to have an inverse, right? So for a function to have an inverse, it must be bijective, right? It must be bijective. Okay, that's on two and injective. Right. What do we know about I inverse? If I were to give you a function like this, let's say I give you a function. Let me give you something familiar. So I give you a function like this, f of x. The inverse of f of x is the reflection in the line y equal to x. Okay? So if I give you any function, all you have to do to get the inverse, once it exists, is reflect in the line y equal to x. Okay? So it's important that we remember that, right? F inverse x is the reflection of f of x in the line y equal to x. All right, there's something important for you to remember. Well, what are the steps again to find inverse? Right, let y equal to f of x, then interchange x and y, then make y the subject, right? Solve for y, and then take that y and make it equal to f inverse x. Okay? All right, so just some small things for you to remember. Please remember that if I give you a relation diagram, when you map from here to here, that's f of x. When you map from here to here, that's f inverse x. Right? You should also remember that how do I get the domain of f inverse x? The domain of f inverse x is the range of f of x. Okay? And the range of f inverse x is the domain of f inverse x. Okay? There's some small things here to remember, right? All right, so that is some things I want you to remember from Form 5. Oh, one more thing, composite functions. So an example of a composite function is f of g of x, right? All f of g of x implies is that we substitute g of x in f of x, right? And there are two popular rules that you should remember. Oh wait, no, you all never did it. Sorry. Right? We need to figure out what this is here, William. Right? We need to figure out what this is. All right, so what's this here? Right? If this is not making sense, I will break it down a little more for you, right? But let's say I gave you f of x, right? Let's say I gave you f of x, and I put f of x into f of x. Where are we? All right, I'm just breaking it down a little bit. I feel that didn't make sense. If it feels some put some there already. All right, let me break it up. A, B, C, and let's take 1, 2, 3. Right, this function is f of x. Of course, here is f inverse x, right? So if I map 1 to A, 2, B to 2, C to 3, right? So if I put A in f of x again, 1. If I put B in f of x again, 2. If I put C in f of x again, 3. That's okay? But if I put 3 in f inverse x, what will I get? See? If I put 2 in f inverse x, what will I get? B, right? So here's my question. Suppose I take f inverse x, right? Suppose I take f inverse x. All of these are f inverse x here. And I put f inverse x, I'm taking f inverse x and I'm putting it into f of x. So I'm taking all my f inverse values. Let's say it's 1, 2, 3. Right? So I'm taking 1, 2, 3 and I'm putting it into f of x. What will I get? Any ideas? You will get ABC, which is what? What is ABC? The domain of, right? So what do I write here? What do I write here? What you will get back? You will get back f of x. Right now, don't lie down. You will get back the y values of, you'll get back the x values, right? So you'll get back x. Okay? So here's what they say. If you take f inverse and you put it into f, you'll always get back x. Right? If you take f of x and you put it in f inverse, you'll always get back x. Right? What I should I do is use real numbers. I'm gonna use real numbers, right? Let's take a function, f of x is equal to, let's take a real function, right? F of x is equal to 2x plus 1, right? Let's take a real function. Let's take the values 1, 2, 3. When I take 1 and put it in there, what will I get? When I put 1 in there, f of 1 will give me 3. Right? When I put 2 in here, I'll get 5. When I put 3 in here, I'll get 7. That's okay? Right. Quickly, top of your head, what is f inverse x? Could you inverse that fast enough? What do you get? X minus 1 on 2. Right? If I put 7 in here, I'll get back 3. If I put 5 in there, I'll get back 2. If I put 3 in here, I'll get back 1. Correct? So what's this here, right? So using our example, what is f of f inverse 3? Right? So let's start. What is f inverse 3? F inverse 3. So when I take 3 and I put it in f inverse, I get back 1. Right? I get it. F of 1. What's f of 1? F of 1 is 3. You'll see that? So f inverse 3 is 1. And f of 1, which is this, is 3. That's okay? So if I have f inverse f of 2, what will I get? f of 2 is what? F of 2 is 5. And f inverse 5 is 2. You're saying that? So generally, what you pattern, right? Generally, f inverse f of x giving me what? Always giving me this x value. You're saying that? Always getting the x value. You see? Saying that? So f inverse f of 2 giving me back whatever x is. F inverse, regardless of how you have it, you're always getting back x. That's okay? So that's what I was kind of trying to show you in the first diagram. So this here is a nice rule that you need to learn. Okay? F of f inverse will always give it back x. Right? Nice little rule there, right? Copy it up. Copy it down and we'll just try a few, right? But those are the things that you need to remember from talk about, right? All right, last one. Try this, please. All right. I found my guy, right? So just write down the two functions first now. Write down the two functions quickly there, right? One. Right, last part is was the relationship between F and G, right? Right. What have you found out? Huh? What's that? Why? Yeah. Right, so F squared means what? Right, X squared means F of X. I hope nobody square X, right? F squared means F of X, so that's F of 2x² plus 1. So that will be 2 by 2x² plus 1 plus 1. So that's 4x² plus 3. That's okay? Easy maths, right? Sorry? I just square in the bracket for sure. Yeah. I got it. Sorry about it. Sorry about it. I was supposed to square it for 2. So it's 2 by 2x² plus 1 all squared plus 1. Sorry about it. right? And then you work that out, right? But the one I'm interested in is this one here, right? You're going to take g of x and you're going to put g of x in there. Okay? So that will be 2 by the square root of x minus 1 on 2 all squared plus 1. Right? When you square root, what will happen? It'll cancel off, right? And then the 2 will cancel with the 2. So you'll get x minus 1 plus 1, which is x. Right? You'll get x. Yeah? Yeah? So here's the problem. Well, not the problem, but what does that mean? If f of g of x given you x, what does that mean? If f of g of x given you x, so it means that g of x is what? It means that g of x is the inverse of f. Okay? So it means that g of x is the inverse of f. That's okay? Alright? So f of x and g of x are inverse of each other. Alright? It doesn't matter. It doesn't matter. So like what? G of x is the inverse of f of x, or f of x is the inverse of g of x. Anyone can do. Okay, but basically it's saying that they are inverse of each other. Alright? Okay? Alright, nice. That is it for today. Alright, so we'll go.